Okay. So hello, I'm Imad, and I'm going to present a bunch of work summarized in this talk called Scaling of Policy Learning, questioning whether it's impossible with outside information. So although I'm the one presenting, many people were involved in this piece of work. So Utman and David from my team, AI for Advertising Research. Anna Corva and Victor Emmanuel, because I'm a PhD student, so those are my supervisors. And Brano from AWS, because kind of the idea started when I was there. Okay, so I'm gonna start by telling you that interactive systems are everywhere, but this is no stranger to anyone here because we work in Criteo and that we have a bunch of interactive systems going on. Then I'm going to explain how we do machine learning in interactive systems and how we scale those machine learning methods. Then I'm going to briefly say what the theory says and what practice says to finally conclude. So although I'm going to talk about what we propose and stuff like that, the really main goal of the presentation is to show how we do machine learning in interactive system from a research perspective, how state-of-the-art looks like. Okay? So yeah, interactive systems are everywhere. So from drug design to manufacturing to online advertising, Criteo, Amazon, Netflix, whatever, we always have this idea of an AI agent, a machine learning model that interacts with users, and it interacts in the following way. So it kind of takes a decision and receives some feedback that depends on how appealing that decision was to the user. So if you think of a recommender system, so the recommender system observes the user, looked at the features of the user and understood that they might be into, they might like football, right? So the recommender system recommends the football. The user actually clicked on the ad. So the recommender system understood that, okay, this user might be into balls. So it recommends a basketball, but got no click. So now it understood that the recommender system actually, the user actually is not that much into balls, but rather likes things related to football. So we recommend a football shoe, and we got a click, and we are happy. So in research in this area, we call these kind of problems as off-policy learning, and it's basically learning when we have an interactive system that operates in the following manner. So first, we have an agent that observes a context. In the case of recommendation, we observe user features. Then the agent takes an action. In the context of recommendation, we recommend a product. And then the agent receives a reward that tells the agent whether the taken action was good for that context. In the case of recommendation, we receive a click, no click indicator that tells us whether the user liked the recommended product. So now that we kind of know how these interactive systems operate and how we model them, the question that remains is how we do learning in these interactive systems, how to learn to improve the decisions of this agent in an offline manner based on some offline data. So we do it the following way. The framework is as follows. So first we have a context. We have in the case of recommendation is a set of features of a user that summarizes their interest, for example. And we have a set of actions. So the agent should choose an action to take. And we have a set of actions to choose from. In the case of recommendations, these are the products to recommend. But more importantly, we have like a login policy by zero. So this is kind of the current strategy of the recommender system. The current recommender system, if its strategy is to recommend the most popular products, this is our pi zero. If it's strategy to recommend the last product seen by the user, this is our strategy. This is our login policy. And why this login policy is important, it's because it's the one used to collect data. So any log data that we have in Criteo is collected by the current recommender system. And the collection happens as follows. First, we observe a context. So we observe the user features, right? Then we take an action. So we recommend a product AI following this policy, following this current strategy, okay? And then we receive a reward, click or no click, based on how appealing the recommended product was for user XI. And this leads to this offline data, this logged data composed of contexts, taken actions, and rewards. The thing is that we don't have the rewards for all actions. So we don't know what would have happened if we recommended another product. We only know the click for the recommended product. And this makes learning very difficult because, well, the thing is that if our Pi0, if our login policy, if our current strategy focuses so much on a very small subset of actions, our data will be very sparse. We won't have all the catalog in the data of products in the data. We will have a very small subset of actions, and learning becomes very hard because of that. So now that we kind of understand, I hope so, the setting, what is the goal? Well, the goal is to find another strategy, to build another recommender system that maximizes the reward, that maximizes the clicks using just the logged data collected by the previous recommender system. So we have a current recommender system. It is used to collect offline data, and then we need to use this offline data to find a new policy, a new recommender system that has better performance. And is it clear? Okay, perfect. So this is like the setting. This is what we want to do. And the main question is, okay, remember that the recommended products are the one chosen by Pi0. So if Pi0 only chooses 100 products from a catalog of 1 million products, our data will only contain these 100 products. And the question that we ask ourselves is, can we find good actions beyond the support of Pi0? So we define the support of Pi0 as the actions, the products recommended by the current strategy. And the question is, can we go beyond that? To give an example, imagine we have like our current recommender system was trained on some historical data, and it can, and historical data didn't contain iPhone 16, right? And somehow our current recommender system only chooses between iPhone 15 with some high probability. It recommends iPhone 15 with like 0.7 probability, and Samsung S24 with 0.3 probability. But we know that iPhone 16 can be cool, and we wonder if we can learn a new recommender system that kind of goes beyond these two actions that we will have in the data, because in logged data, we won't have iPhone 16. So we don't know whether it's appealing or not to the users, right? So this is the main question. So the question is, can we find good actions beyond the support of the current recommender system? And the answer is no. If we just come and try to learn without any site information, we can prove like theoretically that's impossible to do. We can't go beyond the actions that we observe in logged data, unless we have some site information that tells us, okay, this product is similar to this product. You have this product, you have this iPhone 15 in your data set, and we know it's good, but the site information is that iPhone 16 is actually very close to iPhone 15, and it might be a good idea to go explore that area as well. So yeah, sorry for spoiling the answer, but I will explain why. But by looking at this question, what would be, if we put our mind as a researcher, what would be the correct way to answer it? Well, we thought it would be to basically look at all the methods in this area of research and see if they can go beyond the support of Pi0. So we take one method, let's analyze the solution that we converge to. Do we converge to something that goes beyond the support of Pi0, or we are always confined to the actions that are to the support of Pi0, which is the actions that are taken by the current recommender system? And this is what we found, is that by analyzing every method, they all are confined to the support of Pi0. And I'm gonna explain the most used method in off-policy learning. So first I'm gonna explain it and then explain why when we use this method, we can't go beyond the support of pi zero. So remember, our goal is to find a new policy pi. So here it's parameterized pi theta. Let's think about, so pi zero is the current recommender system. Think of it as our current neural network or linear model or whatever we are using. Pi theta is a new neural network that we parameterize a certain way that we think is a good way to parameterize recommender systems. And the idea is we want to find this new p theta, we want to optimize it so that p theta will have better performance than pi zero. P theta will have better reward, okay?
Pi theta includes also parameters over the actions.
What do you mean?
Like, is it just the blender of action? Like, how are the actions and the context represented? Like, what is theta really?
Theta is like, okay, we think of theta as a concatenation of action embeddings. So if we have like 100 products, each product is represented by an embedding, and it's a huge concatenation of product embeddings. And we put all of this in a neural network with the softmax, and that gives us our like recommender system that we want to optimize. But now the embeddings, the idea that we learn these embeddings so that they maximize the reward, right?
Right.
And this is like a very kind of famous method of policy learning. And the idea is simple. So what we want to do is maximize the reward, right? So our estimator will be just empirical mean of the reward. So in our data here, we have xi, ai, ri. Well, we will look at the empirical mean of the rewards and look for the policy that maximizes the reward, right? The empirical mean. So 1 over n sum of ri, okay? But then this empirical mean is weighted by this p theta divided by pi zero. As I said before, p theta is the new recommender system, and we will try to find the argmax over theta. So find the parameters, the embeddings that lead to the highest reward. And pi zero is the current recommender system. And the thing is that what we do here, to understand what we do here, is that we have an empirical mean, but we divide by this pi zero. And to have an intuition, if we go to a room and try to find what's the average height of a person, okay, the main idea will be, let's measure everyone here and look at the mean, at the average. It's easy to compute. The problem is that by doing this, we end up with a very biased estimator. Why? Because by looking here, I see the room is kind of biased to tall people, and more men, challenges of women in tech, more men than women. So when we do just the average, it creates an average that is higher than the actual average in the world. So how to solve that? Well, we solve it by dividing by pi zero. So we know that when we enter the room, we are in tech. So we already know that the portion of men is higher than women. And just by taking this into account, we won't just calculate the average height, but the average height weighted by the fact that we have much more men than women in the room. And by doing this, we end up with a better estimator. This is exactly what we do here, because our data is very biased to the choices of the current recommender system. So we need to debias it by dividing by this pi zero. And so this is the estimator, and I hope it kind of clear. It's the hardest thing to explain in this policy learning thing, but this is kind of what it does. So we can look at it as an estimation of what would be the performance of p theta if it was deployed, and we just take and try to find the parameters, the embeddings that maximize it. The problem is that we can prove theoretically that when we do that, we converge to a policy that, okay, sorry for the math, but what we do is we converge to a policy that takes the current recommender system chooses iPhone 15 with probability 0.7 and Samsung with probability 0.3. What this does is that it will put all the mass on iPhone 15. So it will take the best action in the support of the current recommender system and give it all the weight. We won't do an exploration. So what it does is, this is my current recommender system. It chooses iPhone 15 with some probability, but sometimes it recommends Samsung S24. Now we understood that for this user, iPhone is better. What this method does is puts all the mass on iPhone 15, and that's it. But it can't discover iPhone 16. And this one of the proofs, theoretically and empirically, that one of the one of the widely used methods for off-policy learning can't go beyond the current support of the current recommender system. There are other ways to do it. For example, well, another loss function, you can think of it as, again, parameterizing a new recommender system with some neural networks and using this loss to optimize it. And here as well, with this widely used method, we also end up with a new recommender system that just improves the previous one, but doesn't go beyond its support. So what this one does is basically, instead of focusing only on one action, on one product, it just gives a little bit more mass, but still has some mass for Samsung S24. So this is the current recommender system, and here to learn the recommender system, just put more probability for iPhone 15, but we still have some probability on Samsung S24.
It's interesting that one ignored pi zero too, right?
And it ignores pi zero. Yeah. So this one doesn't care about pi zero. Okay. Another method that widely used in practice now, not in theory, is to say, I'm gonna do a regression. I have my data set of XI, the user features, the products, and the click or no click. So what I'm gonna do is associate each product with a product embedding and say that the product embedding and the user features produce the click. So the click is basically some, let's say, some inner product between the embedding of products and the user features. And what we do is we learn the product embeddings using like some linear regression or logistic regression or whatever we want. Mathematically, we can show this as, we have an action A, so this is the product. We have some embedding theta A that we want to learn, so the things in blue are the things we learn. And we have some X, which is the features of the user, and theta A, which is the product embedding and the user of features, affect the reward, which is in our case the click or no click. And we learn the embeddings, the theta A's, using maximum likelihood estimators. Well, we can show in this case as well that we can't exceed the support of pi zero. We can't exceed the actions that we have in data, because we think of it. We have each product has its embedding, and we want to learn these product embeddings. So what we will do is basically split the data by product and use each splitted data to learn an embedding, because we have like separate embedding for each product. We don't have yet a way to mix embeddings, and to learn the embedding of iPhone 15, we use like the embeddings of iPhone 16 or something like this. We learn each embedding separately. So if we don't have any data about iPhone 16, how can we learn its embedding? So this makes, so this is a problem. And here next we will show how we can actually go beyond the current recommender system choices by using site information. So as we said before, we have like this recommender system interactions, and we have like football, basketball, and football shoes. And the thing is that in general, in practice, we have an embedding for each product, okay? And to learn the embedding of each product, as I said before, the straightforward way is to learn it separately. So to learn the product embedding of a football, we will use only the interactions we had with ads that contain the football. to learn the product embedding of a basketball, we will use only the interactions we had with ads that contained a basketball. And this makes it difficult to learn the product embedding of a new product that we didn't have in data. Well, what we can do instead is use product correlations. The fact that some products are correlated with each other and or similar to each other, so that we can learn more efficiently. The idea is simple. I have only two products in my data set, iPhone 15 and Samsung S24. And I know that I have in my catalog some products that are unseen in the data, for example, iPhone 16. Well, I'm just going to use the fact that iPhone 16 is highly correlated. It's very similar to iPhone 15, with probably more appeal, and has probably more appeal than iPhone 15, given that it's new. So this is kind of the idea of how we can use site information. So if we get back to the idea, before we had like basketball, football, iPhone 16 user features. If we recommend iPhone 15, we use only iPhone 15, and we like use iPhone 15 in user features and predict the click or no click. But what we can do, and this is just an example, this is not like how we do it mathematically, but what we can do is to say, okay, there are some kind of relationships between these products. They are not completely independent. If we think of it, this basketball and football are actually related in the sports category. And iPhone 16 and iPhone 15 are related in the tech category. And when we look now at our data, we don't look at it as, I have some user one, I recommended iPhone 15, and I got click or no click. We see it now as, I have user one, I recommended iPhone 15, iPhone 15 is in the tech category. The tech category also contained iPhone 16, and we got a click. So we kind of mix the data set so that we can go beyond what we have in it, okay? And this is just an example, a very simplified example of how we can use some site information to kind of learn above what we have in the data set. So this is just, okay, we use categories, but we can use much more very complicated models to capture these categories, like diffusion models and stuff like that. Okay, so, but how we do it mathematically? Well, it's very simple. So as we said before we had this, we have an action, so product, it is associated with a product embedding, and we use this product embedding along with the user features to produce the reward. And we learn the product embedding using the interactions, only the interactions with that specific product. Now what we do is we add a latent parameter here. We add a latent embedding that is shared by all action parameters. And this latent embedding will kind of encode the correlations between them. This latent embedding is what will encode the categories, for example. This is the most simplified case, a latent embedding that kind of captures the fact that, oh, these products are mapped in one category and these products are mapped in another category. But we can do much more and let the model learn kind of these very complex dependencies that we might not even imagine. So yeah, when we do that and plug everything and let the optimization does its thing, we get a very good performing model. So now I'm just gonna say in words, not in text, just in text, not in equations, what the theory says. Well, the theory says that, yes, we can go beyond support of Pi0. So we can go beyond the actions that we have in the data set if there are some similar actions. So if we have some similar actions, some actions that are similar to the ones we already have in data, okay? And actually, we can even identify the best action. In our example, it's iPhone 16. If it is correlated or similar to an action that we already have in data, let's say iPhone 15, we already have in the data. We proved that the method is very SOTA in terms of theoretical guarantees, and well, I can't say more. And actually, the theory is very sexy, mainly thanks to my PhD supervisor, to give some credit, which is he is an applied mathematician, but we kind of proved something very good theoretically that was kind of we had an intuition in practice about it, but in theory it was never clear, but now we can show that. And what practice says, I can't show all the experiments, but this experiment kind of summarizes everything. Okay, so here in the x-axis, we have the number of products, the total number of products in our problem. So when the number of products increases, the problem becomes harder, okay? In the y-axis, we have the reward of the learned policy. So the higher, the better. In orange, it's a traditional method, and in red, it's a method that uses site information. And we can see that when we have a very few actions, the two methods have similar performance. Basically, because if you have 10 actions in total, it is very likely that your data will contain all actions. But once the number of actions increases, the gap between the two methods becomes very large.
A question here. So direct method uses this, like how many rewards do you have? Like it's always the same log reward for all the plots?
Or I didn't understand.
Like the data, like
yeah,
like
the same number of samples,
but you spread it differently. Like, are you active learning? Are you basically exploring, or do you have a log data?
Log data fixed,
like the log for pi 0.
Yes,
you have a pi 0 that is of this size.
It's uniform.
And it's uniform, like you sample everywhere in the
epsilon greedy.
Epsilon greedy.
Yep.
And okay, so it's like I don't know, Hapoel arms that are the most and uniform everywhere.
Exactly.
And the direct method, like a Bayesian method with latents, works bad, and then yours works very well.
Yes.
Okay. Now, I want to know what's yours.
Yeah. So that's kind of a summary of experiments, but there are a bunch that we can't present here. So in this work, I mean, these slides were mainly, my goal was to kind of present the framework and kind of explain how people in research understand interactive systems and offline learning in interactive systems. After that, we explain how we can do scaling, how we scale learning in interactive systems from a research perspective, which is quite really like aligned with some of the ideas that we tested also here in a recommendation. And the goal is that the idea was that scaling is actually possible by incorporating site informative priors and site information. My guess, and this is what kind of I will try to explore next, is to use pre-trained LLMs and diffusion models as great site informators, okay? These kind of ideas were published in venues in not only of policy learning, but online reinforcement learning, based on identification, stuff like that. And they will be happy to explain more. If you wish, you can direct me, ping me. Yeah, thank you.
Okay, thank you.
So what is SDF?
Yeah, I didn't talk about it that much, but this is SDF.
It's a hierarchical prior.
It's a kind of encodes the action correlations using a latent parameter.
So it's like blob.
In some sense.
So and then the baseline was not that, it had only
it's MLE, but plus some Gaussian prior.
Okay, but there was no co-occurrence prior.
No. So it's just basically using using site information, using action correlations versus not using.
Okay, so obviously then
yeah.
Okay. So this is borrowing strengths and that's not.
Yes.
Okay. Okay. Thank you.
One more question or anyone?
Thank you.
Well, thank you.
Thank you.
And now LLMs, huh?
Yeah, of course.
Are they working?
Not yet.
Nice.
And you want me to make you
Let's try it without and let's see what happens.
I mean I can do
When you should share this slide.
Yes, I'm coming. Yep.